Before we move into the amphibolite level meta-evaporites in the Domes region or the Northwest Province, I want to spend a little time in this chapter reviewing what happens to halite once it attains the greenschist grade and moves beyond the greenschist grade into the amphibolite realm. Well, what happens to halite is fairly early on in the greenschist realm, certainly by temperatures of 250, 300 degrees, halite starts to transform, and very soon it disappears into a range of metamorphic alteration products, quite often sodic products, including sodic scapolite, whereas anhydrite tends to remain behind. Anhydrite is stable up to temperatures of 1200 degrees centigrade. Halite is not stable once temperatures exceed a few hundred degrees, and we'll see why that is shortly in terms of what happens to its lattice as temperatures and pressures increase. Before we do that, a little bit of Geology 101, having a look at the metamorphic realm. The various metamorphic facies are usually divided up into a depth, pressure, temperature plot along the lines of this diagram, which shows the diagenetic realm occurring once the rock has been posited and is buried and temperature and pressure starts to increase. As that occurs, we pass into the zeolite realm and then a prehnite pumpelliite realm. Beyond that, we pass into greenschist, amphibolite and granulite, or in higher pressure realms with lower temperatures into the blue schist and eclogite realm, or in contact halometamorphism around newly emplaced igneous masses, we go into the hornfels association. So superimposed on this metamorphic realm diagram, we can look at the different styles of plate tectonic settings which define the types of metamorphic facies evolution we will see. In contact aureoles, we tend to see hornfels metamorphism, whereas in the orogenic realm, we tend to see a transition through greenschist, amphibolite and granulite at somewhat higher pressures and greater depths. And then in subduction zones, we tend to see that transition going from zeolites through blue schist into eclogites. We're looking at the Laphalian orogeny, and so we're looking at the types of metamorphic transitions associated with that transition from greenschist to amphibolite. Now, as long ago as 2000, Yardley, in a keynote paper and then a subsequent paper by Yardley and Graham, established quite clearly that metamorphic minerals with an evaporite protolith tend to be enriched in sodium, potassium and magnesium, emplaced in a variety of minerals, and these meta-evaporite minerals can also retain quite high levels of volatiles, so elevated levels of chlorine, sulfur, and also carbon dioxide, along with boron, all of which, along with the high salinity in the associated metamorphic fluids, indicate their evaporitic protolith. The high levels of sodium tend to come from the dissolution and the alteration of halite or trona, the sodic salts, halite in the marine feeds, trona in the continental fed evaporite systems, whereas magnesium tends to come from earlier diagenetic magnesian minerals, such as the reflux dolomites or the various magnesium-rich evaporitic clays that we see in many meta-evaporite associations. However, once the evaporites, especially the halite, is altered, transitioned into a variety of metamorphic minerals, the direct evidence of a sooty protolith is largely removed. That's why various processes of fluid dispersion and ongoing loss of volatiles, and then the paleoevaporitic indications that we see in our metamorphic evaporite associations are generally textural. Textural relics of breccia beds, thrust welds, ruwaks, and or salt welds and fault welds. Sometimes we see in the early stages of transformation widespread sodic phlogopites, along with widespread sodium aluminum talcs in a variety of saline metapelites. Quite often we can have in various tourmalinites elevated levels of boron, which may have come from a variety of boron salts such as colemanite and eulicites, especially in lacustrine protolith. We may see evidence preserved of the protolith as pseudomorphs. For example, there are sodic scapolite dominated sequences in the Cordillera in the Batik of Spain, which preserved sulfate crystal outlines of both gypsum and anhydrite. We may preserve anhydrite. Remember I said anhydrite is stable in the metamorphic realm up to temperatures of 1200 degrees, and so we see massive anhydrites in the Grenville Precambrian province of North America, along with a range of stratiform anorthosites and albertites, all of which have been interpreted as possible indications of a evaporitic protolith to our meta-evaporitic association. Likewise, the various anhydrite-containing mesoproterozoic silicates in the Oakian granulite complexes in southern Mexico, and I would argue also the pervasive scapolites in the domes region of the Zambian copper belts, indicate an evaporitic protolith. In a key diagram published by Yardley and Graham back in 2003, they showed the evolution of these brines as we go from the diagenetic realm, temperatures of less than 200 degrees, to greater depths, and the associated sodium chloride content in the fluid inclusions in these devolving successions. You can see there is a broad range of salinities in the diagenetic realm, indicated in blue, temperatures of less than 200 degrees. And we can see that in the more saline systems, as we have, for example, brines in the Permian evaporites, number 1, or the saline southern zechstein-associated North Sea formation waters, we see quite high salinities in our fluid inclusions. And those high salinities are inherited as we go into the metamorphic realm. So, for example, in the Pyrenees, where we have salt-lubricated thrust belts, we see the quartz veins retain quite high levels of sodium chloride, as do the various emerald-bearing veins in evaporitic metasediments in the Colombian emerald fields. Similarly, the meta-evaporitic Damara belt metasediments in Namibia retain these high levels of salinity, and there's a segregation there in the Damara between those areas which had an evaporitic protolith and those which had a non-evaporitic association. Likewise, we can see in Vermont the high levels of salinity in those inclusions, quite often associated also with massive anhydrites in the Gravellian terranes in the northeast US. Yardley and Graham argued that this temperature salinity plot for the inclusions and the associated salinity levels in the formation waters and the metamorphic fluids, this is restricted to protoliths which were deposited in shallow and continental margin sedimentation styles. We can see there is an inheritance of high salinity in the brines coming out what was an evaporitic precursor. High salinities are often inherited from the original high salinity basinal brines in our diagenetic realm as we pass into the metamorphic realm. It's interesting also if we look at the area of the rectangle enclosed in A, that indicates the low salinity fields for formation waters, springs, and metamorphic fluids that are sitting within oceanic or accretionary prism waters where we did not have high salinity in the original basinal fluids. And we see the inheritance of those lower salinity waters in the syn-metamorphic quartz veins, number 10 in the Halite dome, or in the metasediments in the Lukmania Pass in Switzerland, or in the veins in Maine in the Waterville Formation or the Sangerville Formation, where we don't see elevated levels, likewise in the Dalradian metasediments in Ireland. However, there is also a dehydration trend as we pass into the eclogites pressurized release of high salinity waters unrelated to evaporite. So not all high salinity waters in the metamorphic realm have to come from an evaporitic precursor. It is a common association, but it's not the sole association with high salinity waters in the metamorphic realm in the high temperature subsurface. There's another fundamental transition that happens when we pass into the greenschist realm, and that is what happens to halite as we pass into the temperatures related to the greenschist realm. So as we pass from temperatures going from less than 100 degrees to more than 100 degrees. This transition of halite as it pressurizes and it changes its crystalline form with burial explains why we get a pulse of sodium chloride-rich waters and the transition of halite to scapolite as we move into the greenschist realm. This comes from a paper by Lewis and Holness, and it reinforces the notion of Yardley and Graham that many chlorine-rich hydrothermal fluids in the deep subsurface are related to the recycling and the alteration of sedimentary halite as it passes into the greenschist realm and beyond. What Lewis and Holness in a paper in 1996 established was that buried salt bodies that have been exposed to high pressures and elevated temperatures become permeable. I'll say that again. Halite becomes permeable as it passes into the greenschist realm. And that's because the crystalline structure of deeply buried halite changes its dihedral angle with compression. Normally, we have crystals of more than 60 degrees dihedral angle, and then as we transition into the higher pressure, higher temperature burial realm, the dihedral angle on those halite crystals attains values of less than 60 degrees. Once that happens, instead of having isolated intercrystalline brine positions, we establish a permeability meshwork or framework which allows pore fluids to move through salt. So if a salt unit was acting as a seal prior to this transition in the dihedral angle, once the dihedral angles have changed, that salt becomes a relative aquifer as we pass into the metamorphic realms. So this transition in dihedral angle begins at the onset of greenschist temperature pressure conditions. It occurs as highly saline hot brines form continuously connected stringers in or around altering and recrystallizing salt. It forms what is a polyhedral permeability meshwork, and that allows hot dense brines and gases to migrate through what was previously the salt seal, and ultimately that will dissolve the salt seal. And so at this stage, as we transition into the greenschist realm, the halite disappears and we release a pulse of sodic and chloride-rich fluids into the metamorphic realm. One of the common products that form from this pulse of fluids is sodic scapolite, along with a range of other metamorphic indicator minerals. At the end of this transformation process, it means by the time we attain temperatures of 300 degrees centigrade, little or no halite remains. That's even though the melting point of halite is 800 degrees, this polyhedral-dihedral transition drives the disappearance of halite at temperatures of less than 300 degrees centigrade. If you want to read more on this, I suggest you go to my book, which accompanies this course, and have a look at the chapter on meta-evaporites, and I discuss this transformation process in more detail. One of the outcomes of this transformation process is the formation of sodic scapolites. Let's go back and have a little bit more geology 101 and talk a little bit about scapolite. And so scapolite, like feldspar, actually describes what is a solid solution series. As we go from albite to anorthite as a solid solution series, we also have mariolite, mahonite as a solid solution series, where in scapolite, the sodic chloride-rich end member is mariolite and the calcium carbonate-rich end member is mahonite. And there's another form, which is the sulfate ion in that magnetic form. So you can actually think of this solid solution series in terms of its compositional variation. We can take 3 moles of albite and 1 mole of sodium chloride, and combined we will make mariolite, the sodic scapolite. Or we can take 3 anorthite feldspars and add some calcium carbonate, and we will get mahonite. And if we add some calcium sulfate to anorthite, we will get a sulfur-rich mahonite. But that sulfate ion shown in the mahonite form is usually more than a trace, even in meta-evaporitic associations, but higher levels are found in the evaporitic association compared to the non-evaporitic associations of mahonite. And also in association, we will see elevated levels of fluorine and hydroxide with that meta-evaporite transformation in the scapolite lattice. Quite often, not exclusively, but quite often, mariolytic or sodic scapolite is a common indicator of passage into the greenschist realm in our meta-evaporitic association, related to that transition into polyhedral porosity as the dihedral angle on the salt interfacial angles lessens with temperature and pressure. The lower diagram is showing us a plot from Ellis back in 1978, where he established a correlation between scapolite composition and fluid composition in laboratory experiments at 750 degrees centigrade and 4,000 bars. And from it, he extracted lines of equal sodium chloride to sodium chloride plus water in the coexisting fluids. The actual measurements that he made in his laboratory created scapolites is shown by the red dots. Now, what that plot is implying, and I'll use a modification to this when we look at scapolites in the domes region, that's showing us that most chloride-poor natural scapolites coexisted with fluids low in sodium chloride, whereas regional occurrences of chloride-rich scapolites, the mariolytic scapolites, are likely to represent metamorphosed evaporite sequences. Now, that's not an exclusive relationship. You also need to see the appropriate textural, the relic textures, indicating we once had the presence of evaporites. It's also interesting that once we form scapolite, we can continue to produce sodium chloride-rich metamorphic fluids as that scapolite is compressed as we go into increasing metamorphic grades. The upper diagram is a bar 100 projection of merolytic scapolite structures, and it's showing you the cage-like structure within the lattice and the linkage of the silica sodium oxygen tetrahedra that parallel the C-axis. The lower image here is the 001 projection of the same crystal structure for merolytic scapolite, and the small circles are representing the cations, sodium in red, and the larger circles in blue are representing the anions, the chlorine. And the arrows around those structures are indicating the sense of rotation of the four-membered tetrahedral rings as we increase the pressure. And of course, what that does as we squeeze the scapolite lattice is that it allows the sodium chloride that's held in those cages to be compressed, and so it will supply sodium chloride into the adjacent metamorphic fluids. So scapolite or metamorphic scapolite continues to be a source of sodium chloride beyond the formation of the initial merolytic scapolite as we compress that scapolite lattice, passing into higher metamorphic grades. Okay. Finish this off, I just want to look at an example in the Cloncurry district of Queensland, which is an obvious meta-evaporitic, widely documented meta-evaporitic scapolite association. So this is the Corella Formation. There's also the Staveley Formation. This is what is called Domain B scapolite in the Corella Formation. Also in the Staveley Formation, it's often associated with breccia units. And so the brown here is indicating deformed, sheared breccias with a variety of albite clasts along with ironstone matrix. Purple unit is showing you the intimate association of the scapolite chlorite biotite rock with those breccia units. This is typical association we see. Breccia in association with scapolite is a good indication of former meta-evaporitic associations for the scapolite. And so in this area, for example, in the Staveley meta-evaporitic welds, we see early widespread sodic and calcic metasomatism, hosted in a variety of quartz, albite, scapolite, actinolite metamorphics. Locally, we see elevated levels of potassium and iron metasomatism, hosted in biotite, magnetite, hematite, quartz, pyrite associations. And then we see the mineralization association, the copper-gold association, where we see associations of quartz, anhydrite, barite, calcite gold, chalcopyrite, bornite, chalcocite, chlorite, muscovite. It's interesting also here that we don't pick up the anhydrite at shallow depths or in outcrop because that anhydrite has been leached by the weathering profile. It's quite a deep regolith in the areas of these deposits, but at depths of more than 400 to 500 meters, the anhydrite remains. Whenever we see a breccia in association with scapolitic associations, we should always ask the question, what's the nature of that breccia unit? Is it a tectonic breccia? Is it an evaporite dissolution breccia? Is it a thrust weld breccia? Is it a salt weld breccia? Where did the gigaclasts in association with this breccia, in this now sheared breccia, come from? This is a section from the Stara copper-gold prospects and deposits in Queensland, and you can quite clearly see there's a 1.5% copper grade equivalent shell in there in the crosshatch zones. It's intimately associated with units adjacent to that breccia. Now, metamorphic geologists call all breccias that they think are sedimentary sedimentary, but of course we know that there's a range of breccia timings all the way from sedimentary alistostone breccias through to halokinetic salt ablation breccias, and we need to differentiate those different styles in the system. We also see in association with this very strong myelinitic fabric, sheared fabrics, possibly sheared at levels of former meta-evaporitic associations. Now, I'm not going to go any further detail in this. I refer you back to the meta-evaporites chapter in my book if you want more detail on these meta-evaporitic associations. But the last comment I want to make, what does a former salt-focused world look like at amphibolite grade? Well, this is what it looks like in the Staveley and the Corella Formation, where we have a series of layer-parallel scapolite-rich metasiltstones. And in association with that, in what has a magnetite matrix, we see these albertized and sheared clasts, along with a variety of siltstone clasts with a calcite matrix, in what was an original salt-lubricated thrust weld. And of course, in association with this, we also have hydrothermal anhydrite, not an outcrop because it's been leached by the modern weathering processes in the regolith, but at depths of more than a few hundred meters, we also have hydrothermal anhydrite associated with these mineralized zones. And there's also some indications in the inclusions of this type of association. And so regionally, when we look at this Cloncurry district, which is the meta-evaporitic association, versus the more regional distribution of inclusions in a variety of hosts in the Mary-Kathleen fault belt, we can see that the Cloncurry district tends to have relatively elevated chlorine levels, both with respect to its iodine-chlorine association and its bromine to chlorine association, giving us pretty good indications that we are looking at a meta-evaporitic succession with a variety of fractionated halogenic signatures that are characteristic of fluid interactions with a meta-evaporitic scapolite association, quite distinct from the associations we see with I-type granites with much lower chlorine levels and hence much higher iodine levels. That's what happens to halite. It tends to evolve into a range of sodic minerals. Evaporite systems in general supply sodic and potassic systems as they move into the metamorphic realm. And quite often, as we evolve our halite, the dihedral angle changes. We get a pulse of sodium chloride-rich brines moving into the system. And so we see a lot of chlorine-rich and also some magnesium-rich phases forming in association with our meta-evaporites. We can't make an unequivocal interpretation unless we also have meta-evaporitic textural indicators such as breccias and so on. And it's that layered concurrent nature of the breccias with the scapolite association that tends to reinforce the idea that we're looking at a meta-evaporitic association in these highly evolved amphibolite level systems, as we see also in the Domes region or the northwest province of Zambia.